All right, so number 11, and I had to shovel this morning, so I'm in my comfy clothes. Let me just back this one up. There we go. Just wanted to make sure that it was an actual video. So here we go.
Hello everybody. In this video we are going to be looking at the solutions to the honors magnetism homework problems 1 through 5. Well, let's get started.
So maybe an honors
Number
high school
1
course? I'm
asks,
not sure.
what is the magnitude of the force per meter of a length on a straight wire carrying an 8.40 amp current when perpendicular to a 0.90 Tesla uniform magnetic field? And we can assume that the length is 1 meter.
All right, so right away, some super awesome stuff here. Sorry, you can't quite see. So first of all, it's asking for force per meter, and then later it says, well, the length is 1 meter. So really, you're just looking for the force. But it's totally extendable, right? Like every single meter of this straight wire is going to have the same force. But a couple of things. First of all, oh my gosh, an 8.4 amp current and almost a Tesla magnetic field. I'm expecting monster numbers here. Because you're not going to experience too much in your life, and frankly, you're not going to experience this too much in your life either. So I'm curious to see how that pans out.
So let's take a look at what we are given here. We are given the current going through the wire at 8.40 amps.
All right, so he's got his results kind of typed up, but he's going to slowly reveal them. Tried and true, right? Teachers have been doing this for years, overhead projectors and sheets of paper. Sometimes you do it at a pace that you want your students to be able to take notes. I'm guessing this is not for students to take notes. It's really just to sort of explain. And obviously, if you were to show everything at once, it would be hard to follow. Now, I always encourage students to use their pointer of some kind to let me know where they're looking when they're talking. But this works too, right? Because obviously the next thing that he reveals is going to be what he's talking about. And already some interesting color use here. I'm always interested in color coding. Well, we're going to write currents in red, and we'll do magnetic field something else, because maybe if he ends up drawing a vector, image, would it be the same color?
I am given the magnitude of the magnetic field at 0.90 Tesla. And I'm given the angle of 90 degrees because I am told that it is perpendicular. So that tells me that is 90 degrees.
So I just played the role of the student. I was like, huh? I didn't see 90 in the problem, right? And I didn't see a theta written down anywhere. But sure enough, there is a very, very helpful word in the problem itself. This word perpendicular is going to provide this. And of course, those of you sort of used to magnetic problems, that's going to make things relatively straightforward. A great follow-up question would be almost word for word the same, but just make this the word parallel. And suddenly you're like, huh? What? Huh? So I love the fact that he took an extra piece of information and immediately converted it. This is another representation, right? This is one representation of what's happening. This is another representation of what's happening. And I think that it's great that that's all there.
My unknown is actually the force per meter. Remember, this is force per meter, which is the length of wire. So the length is 1 meter. So when I want to solve for force per meter, I start off with F equals ILB times the sine of theta. I divide both sides by the length. And when I do that, I am going to get the force divided by the length, or force per meter, on one side of my equal sign. And that's going to be equal to the current times the magnetic field times the sine of the angle. So I plug in my known values.
So this is really cool, right? So this is the standard way of calculating force. And since it was a 1 meter long wire, he could have just plugged all that in and said, well, if that meter gets it, every meter gets it. But he's being very explicit, right? He's saying, no, well, if this is the force, then this is the force per length. It's just the current times the magnetic field. So when he plugs it all in, he gets 7.6 newtons per meter, which actually is not the monster number I was thinking of. But I would guess, let's see. So if you've got 7 newtons on a little wire, a meter of wire is going to weigh what? Well, a wire that can carry 8.4 amps might weigh a lot, but let's say it's just a tiny little wire. The wires that they deal with in class. So I don't know, 50 grams or something, 0.05. So F equals ma, a equals f to yeah. So that's quite a bit of acceleration. Lots of g's that thing's going to feel if it's a wimpy wire. But of course, a wimpy wire is going to die if you put 8.4 amps of current through it. So it's really interesting how things end up sort of balancing themselves out. I don't know why my screen's shaking. Sorry about that.
Values for current and magnetic field and my angle of 90 degrees, and I'm going to get a force per meter of 7.6 newtons per meter. The second part of the problem asks, what if the angle between the wire and the field were only 45 degrees?
So it's really interesting, right? So very, very likely when this was given to the students, A and B were written right next to each other. So to not even show B yet, to sort of say, okay, let's do some A stuff, let's figure out what it's doing, to not even get students worried about part B until it's needed is interesting. Now, what do we expect here? Well, it's going to be less because the sign is going to come down from 1, it's going to be square root of 2, which is 0.7. So 0.7, I don't know, about 5 newtons per meter.
So I'm going to solve the same exact way. I'm looking for the same thing. What is my force per meter? And only in this problem, I'm going to replace my angle with 45 degrees. So 8.40 amps times 0.90 Tesla times the sine of 45 degrees is going to give me a force per meter of 5.3 newtons per meter.
So it's interesting. If it goes all the way to parallel, it goes all the way out on 0. So you could call 45 degrees halfway, right? So 90 degrees was 7.6. Halfway down to 0 is still 5.3. And so that's how these trigonometric functions work. They don't just zoom ramp down to 0. They whoop down to 0, which means we're still kind of up here and a healthy amount of force, even though you've made half the amount of change you could possibly make from 90 to 45 degrees. So I think that driving that idea home with students is really interesting.
You know, one of these days I'm going to make a blooper reel from all these videos I've been making. What you're seeing isn't very polished, but usually by the time I get to what I'm presenting to you, it's taken several attempts or several takes for me to get to this point. So it's kind of sad when you think about it. You think after 53 years I'd have a better command of the English language, but I guess you guys should know better than most that I don't. All right, anyways, let's move on.
Wow. So, I love it when people sort of display their humanity in these videos. And what he's done here is really, really interesting. So he's pointed out that it's all typed up nicely for him, and sort of got down to the answer really quick. And he says, even after having done this for so long and having taught this for so long, I still have to sort of, fiddle with it for a little while before I feel comfortable with it. Now, he needs a different level of comfort, sort of to present it and make a video on YouTube that some loser is going to make a reaction video to, right? Whereas the student's threshold is just get it done. But I think it's helpful for students to realize that that's what's happening, because they can think sometimes that the teacher is just sort of magical, just plows through and never makes mistakes.
Let's move on to problem number 2. We want to calculate the magnitude of the magnetic force on a 160 meter length of straight wire stretched between 2 towers carrying a 150 amp current.
Oof.
The Earth's magnetic field of 5.0 times 10 to the minus 5th Tesla makes an angle of 65 degrees with the wire.
Okay, so it's a huge
the
current.
length of the wire at 160
a tiny little
meters,
magnetic field.
Given the strength.
That Earth's magnetic field, what is that? Half a Gauss? Is that what that is? Yeah, because a Gauss, I think, is 10 to the minus 4, right? It's this tiny little thing. You wouldn't think we notice it. And yet, we know that so much in our world can feel it, can navigate with it, you can find evidence in rocks. There's all kinds of things. So even that level of magnetic field can do interesting things. So 160 meters between 2 big towers. I'm thinking about driving on the highway. So a football field and a half, a soccer field and a half between towers. Okay, yeah, that's huge towers. 150 amps. I don't know. I don't know what those gigantic power lines carry. I know they're usually at a really high voltage. So I suppose 150 amps could be reasonable. So what do we expect this answer to give? Like, how much does the magnetic field make the wire sway? I'm going to guess not much. I'm going to guess less than a meter.
Strength of the current at 150 amps. Given the
so hang on a second. All we're going to get here is force. How would I know if it's enough to make it shift? We'd have to know how massive it is. Shoot. right? So here's an example. I don't really know how to make this estimation. So because I don't know how massive the wire is. Now, I could take some time right now and really rack my brain. So what the heck, I'll do it. 160-meter long wire that's thick enough to carry 150 amps. I'm thinking one of those massive spools, multiple tons, right? And then, so let's say it's 2,000 kilograms, right? That'd be 2 tons. So 2,000 kilograms. Then I want to see if the force that it's experiencing is sort of compared to gravity. And I'm expecting it not to be very much compared to gravity. So gravity would be 20,000 newtons. So I'm expecting this to be less than 1,000.
Given the strength of the magnetic field, this is the Earth's magnetic field, at 5.0 times 10 to the minus fifth Tesla, and the angle between the magnetic field and the current is 65 degrees, and we are being asked to find the force. The good news is we don't have to rearrange our formula. F equals ILB sine theta.
Oh my gosh.
We're already solved for our unknown. So I simply need to plug in my known values and multiply them all.
A couple of things. I was way off. I said less than 1,000, so technically right, ding, but way less than 1,000. This has got to be like nothing. So this is comparable to a bird landing on it, right? Let's see, a bird, less than a kilogram. Yeah. This is like a bird landing on it. So, wow, so small. Second thing, to jump to the whole thing, the last thing that he flashed on the screen is this entire thing. And I'm trying to think through like the students, especially the students who knew what was coming, right? Yeah, well, it's the same equation we've been doing for all our other homework problems. They can see the whole thing, including the answer. Even though now he's walking us through the calculation, I think it's useful to show the whole thing. I mean, I could see it either way. You slowly show that this entire line. But for the students who really want to, they can jump to the end. For the students who are lost, they can say, "Wait a minute, how did you get that?" So I actually think this is cool.
All together, 150 amps times 160 meters times 5.0 times 10 to the minus fifth Tesla times the sine of 65 degrees is going to give me a value of 1.1 newtons. Problem 3.
All right, so I'm going to stop there. Wow, really, really cool stuff. I love the crack he made about the blooper reel. I love the way that he's sort of slowly displaying the stuff, and the occasional drawing of a picture, or drawing. He wrote F over L at one point. I think that these kinds of problems can be tricky, and I think that trying to do some estimations, it was sort of fascinating for me to be way off on my estimations, but the results, I think, are really, really interesting. So that's it for today, everybody. Thanks. And remember that physics teachers are awesome.